design of this AB in the left. Now, if and hello students, welcome to my YouTube channel VRacademy. We have completed SR flip-flop in the last video, and we'll be going for D flip-flop in this video, and we'll be trying to complete it in the same fashion that we have done in previous case. I mean, during the SR flip-flop explanation, I have told you I'll follow the process. The process was, first I'll go for design. From design, I'll go for a Boolean expression. That Boolean expression will help us to go for operation. Then from operation, we'll be able to design the truth table. From truth table, we'll be able to get the characteristic table. Then characteristic equation will be derived with the help of characteristic table. After getting that characteristic equation, we'll be going for excitation table. That excitation table will be designed with the help of characteristic table only. And finally, we'll be going for the state diagram, which will be designed with the help of either you can go for characteristic table, or at best you can go for excitation table. That will be very, very easier. Now let us start the processing and let us start D flip-flop. So coming to D flip-flop, the first thing is what exactly D stands for. D stands for either delay or data. I mean, D flip-flop is either called as delay flip-flop or data flip-flop. Why it is called as delay or data flip-flop? Because it is only, you can see that there is no migration in the input to the output. Only the delays are being provided by the different gates that are present inside its design. And there is no change from inputs to the output, because if you are giving 0 input, you will be getting 0 output. If you are giving 1 input, you will be getting 1 output. So therefore, either it can be used for storing as a data, or it will be providing a particular time delay that is required in certain condition or certain circuits. So that is why it is also known as delay or data flip-flop. Now coming to the design process, I have said you in the last video that SR flip-flop is the most important flip-flop that is going to decide the design of other respective flip-flops. So once you know SR flip-flop, then by using that SR flip-flop, we'll be able to design D flip-flop. How to go for D flip-flop using SR flip-flop? Just draw the SR flip-flop as I have said you in previous video. Just draw that, taking two NAND gates and making the upper NAND gate as, or you can say the upper terminal of G1 NAND gate as longer, then lower one as smaller. Then for G2, you make the upper one as smaller, the lower one as longer. Just connect that to give the clock. Then that terminal will be S, lower terminal will be R. The output of G1 will be given to G3. Output of G2 will be given as G4. The other terminals of G3 and G4 are kept in such a manner, and you should be drawing a perpendicular at the input and the output and writing a cross X. And after writing that X, you will be able to get the overall structure of SR flip-flop. The only change you have to make in designing a D flip-flop using SR flip-flop, that you have to connect S and R terminal via a NOT gate. It is written over here. It will be designed with the help of SR flip-flop just by joining S and R terminal via a NOT gate. If you are joining that one, you will be getting the D flip-flop. Now once you have got D flip-flop, next is to go for Boolean expression. Now for getting the Boolean expression, what I have done, I have taken this one as X and this one as Y. Even a student who has just gone for starting the digital electronics, he can also write the Boolean expression for this X and Y. What is that? D is from here, clock is from here. So D dot clock whole bar. Similarly, for this is D bar clock whole bar. So X value is D dot clock whole bar, Y value is D bar dot clock whole bar. Just use De Morgan's theorem. This will be D bar plus clock whole bar, D plus clock whole bar. Now, after that, we have taken a condition that if clock is equal to 1, then X equals to D bar, Y equals to D. Why I am taking clock equals to 1? Because we know that if clock will become equals to 0 during this condition, then this value will be 1, this value will be 1. That means it will not be depending on D input. So it is not like that. If your output is not depending on input, what is the meaning of doing all those things? So therefore, we have to take clock equals to 1. Now if I am taking clock equals to 1 and if I am solving it, we are getting X equals to D bar, Y equals to D. That is what I have written it over here. If you will put 0, I mean if you are putting clock equals to 1, you will be getting X equals to D bar, Y equals to D. Once you have got that, go for Q. For Q, you can see that it is we are using an AND gate. Here it is X, here it is Q bar. So it is X dot Q bar whole bar. So that is what I have written, Q bar dot X whole bar. Just gone for De Morgan's using a De Morgan's theorem, and we have got Q equals to Q plus D. Similarly, Q bar will be Y dot Q whole bar, that is Y bar plus Q bar, that is nothing but Q plus Q bar plus D bar. So final expression that we are obtaining is Q equals to Q plus D, Q bar equals to Q bar plus D bar. Now, after that, we have to go for, because here we are having only one input, so there are two cases of operation. One is D equals to 0, other one is D equals to 1. So if I am putting clock equals to 1, which is obvious, and D equals to 0, by putting these two values over here, you just put up D equals to 0 will give you Q. If you are putting D equals to 0, you are getting 1 for this. So Q bar is coming as 1 and Q is coming as Q. Now since we have got Q bar equals to 1 right now, that will be complemented to give the value of Q. So that is 0. And this condition will be described as reset. This condition will be described as reset because Q value is coming out to be 0. Now once you have got this, go for case 2, that is clock equals to 1, D equals to 1. Clock equals to 1 is mandatory, D equals to 1. Substitute that value in your 1 and 2. So Q you will be obtaining in that case equals to 1. It is obvious because if you are writing Q equals to Q plus D, Q plus 1 will give you 1. So therefore Q is equals to 1. And similarly Q bar will come out to be Q bar, that is nothing but simultaneously you have got Q value equals to 1. So the complement of that one will be 0 and you will be getting Q equals to 1, and this condition is described as set condition. This condition is described as set condition. Now after getting this operation done, we'll be going for the truth table. Truth table is very simple. We have to go for a clock, input D, then Q, Q bar, and finally we have to go for remark. Now clock signal is down. I have already said you, once clock signal is down, nothing is dependent on input. So that is why I put a cross and operation will not start at this position. Once clock signal is high, that is 1, then there are two cases of input, that is 0 and 1. And we have got the output in this case. When D is 0, we are getting Q as 0, and Q bar equals to 1. When D is 1, we are getting Q equals to 1 and Q bar equals to 0. Output is 0 means reset, output is 1 means set. So that is your remarks. Once you have got this, you have to go for characteristic table. Now you can see the characteristic table definition. It is written that it is a table that consists of present state and the inputs of the flip-flop. Present state and the inputs. Right now it is having only one input, so I have written D, along with the respective output, that is next state. So next state is Qn plus 1. Now if you can see it, if we are having two inputs, we can have 4 combinations, 00, 11, 01, 01. Now once you have got that, by using this truth table, you will be able to write it. Now primarily, when you are going for writing the next state, you need to follow or you need to concentrate on the input first. Nothing else. You need to concentrate on input. So if D is 0, what is the output? Reset. Reset means 0. When D is 1, what is the output? 1. When D is 0, output is reset. When D is 1, output is set. That's it. There is no dependency of D flip-flop on the previous state. Therefore, we are writing like this one. Now once we have got the characteristic table, we need to go for characteristic equation. But it is obvious that it is the binary equation or Boolean expression. Don't write binary, write it as Boolean expression. It is a Boolean expression. It is a Boolean equation of next state of the flip-flop in terms of present state and the input of the flip-flop. So for that reason, because we are having two input, we are going for two variable K-map. We have written it Qn bar Qn and just put the value of Qn plus 1, 0, 1, 0, 1, 0, 1, 0, 1. We are having only one pair out of here, and that pair is giving us the value of Qn plus 1 equals to D. Now once we have got this, we have to go for excitation table. Excitation table, I have already said you in the previous explanation, and here also it is written, it is a table that has present state and next state serving as the input and output. With the help of those values, we determine the response, that is input. So initially, I am just rubbing it so that it will become more easier to you to understand. If we are having present state and next state, so combination we have written 4 combination, that is 00, 11, 01, 01. Now you just see the characteristic table and from there you try to fill it out. Present state 0, next state 0. What is the value of D? 0. So present state 0, next state 0. What is the value of D? 0. Present state 0, next state 1. What is the value of D? 1. So we are writing it as 1. Present state 1, next state 0. What is the value of D? 0. We have written it 0. Present state 1, next state 1. What is the value of D? 1. Write it as 1. So this is your excitation table. Now last one is state diagram. I have said you it is the pictorial representation of change of state with all the transitions shown in with the help of arrows. So we are having, definitely if we are having only one flip-flop, there are two states, either 0 or 1. So we have taken 0, we have taken 1, just bubbled it up so that we can tell it that both are the state. Now see here, from here 0 you are moving to 0. What is the input at that time? 0. So 0 to 0, 0 to 0 at that time, what is the input? 0. Then 0 to 1, 0 to 1. What is the input? 1. 1 to 1. Yeah, 1 to 0. 1 to 0. At that time, what is the value? 0. What is the value of D at that time? 0. And 1 to 1. 1 to 1. We are having the value equals to 1. So we have written it as 1. That's it. So this is all about the D flip-flop. I think you have got the explanation. Because I am following the same trend that I have used in case of SR flip-flop, it is very easy to understand. Next, this is all about the D flip-flop. If you have any doubt and suggestion, you can come up with that. But this is the best way one can explain each and everything about the D flip-flop. Come up with your suggestion in the comment box. It will be very helpful for me. Thank you very much.